In this exercise, we have a fork of a previous problem linked below, number 7, where we did something like this, where we had a bunch of these circuits, the same exact amount. However, the table that we were given, which is this right here, was incorrect for that problem. And the reason why it was incorrect is because the P absorbed and the P delivered did not equal 0. In this problem, our P absorbed and our P delivered does equal 0. So that means we're just going to fill in all of these P's, all of these powers. P is power, P ABS is P absorbed, and P DEL is P delivered. Again, this must equal 0 for this to be a complete circuit. The power going into one of the circuits must equal the power going out of the circuit. And the formula that we are going to use, the general formula we are going to use for this, is that power is equal to the voltage times our current. We are given current in milliamps, and it's asking us for milliwatts down here in our answers, so we don't have to do any converting. Normally we would be multiplying volts times amps, but here is totally fine. So now we are going to start off the first problem. We're going to go down the list and continue doing this. Something that might help from the notes is this explanation right here, where we are told about positive values and negative values. We also have to remember, and it was explained in problem 7, that negative values and positive values only denote direction. They don't actually denote positivity or negativity. What does denote positivity and negativity is the absorption and delivery. Delivery being negative because it's being delivered out of the circuit, and absorption being positive because it's being absorbed into the circuit. So the first thing we're going to do is start with P subscript A. When we look at what we're given, we have our voltage right here and our current right here. Both are positive, so all we're going to do is look at this circuit right here. So we know that our voltage goes through the positive and out of the negative normally. So it's going to look like this. This is how the voltage drop works. It goes from our terminal 1, which is positive, into the terminal 2, which is negative. Now our current right here is going against our voltage. This means that we are going to have a negative value. So when we set this equal, we are going to first throw a negative out front, and then inside of here we are going to multiply our voltage, which is 1.6, by our current, which is 80. And then we are going to get a voltage times milliamps. For P of A, after plugging this into a calculator, we are going to get 128 milliwatts as our answer. Next, we have B. Looking at B, our current and our voltage is both positive, so we're just going to look at the actual circuit. So looking at our circuit, we know that our terminal 1, which is positive, is on this side, terminal 2 is on this side because it's negative. So that means our voltage is going through the positive and out of the negative. This is also going in the opposite direction of our current. Our current is going this way, and since it is like that, we're going to have another negative. So we're going to have our PB, or power subscript B, equal to a negative, because it is delivering 2.6 times 60. And after we plug this into a calculator, we are going to get negative 156. Next, we have C. And for C, we have the voltage as negative and our current as negative. So we're going to have to look at this table for a deeper explanation, but I'm going to give just a super diagram, easy explanation of this. But when we do C, normally we know that our voltage goes into the positive and out of the negative. If we have a negative, we are just going to reverse this. So instead of going this way, we are instead going to go this way. So we're going to go into the negative, out of the positive. Now we know that our current is negative. So our current is going this way, but the part that matters is going this way. And since our current, the part that matters, and the voltage is going in the same direction, that means our power C is going to be a positive. So inside of here, we're going to have 4.2 times 50. So to give a more technical explanation of this, we have our circuit, we have 1, this is our 1, this is positive, and we have 2, it's going this way, this is our voltage, and our current is like this. So in this example, we have a negative value for our voltage. So we're going to have a voltage drop from terminal 2 into terminal 1, because we know our voltage is going like this. Next, we have a negative current, and since our current is actually, it's going this way, even though I said the part that matters is going this way, we're about to see why the part that matters is going to the left instead. So the part that matters is going to the left, because when we look down at this area right here where we have the I for current, we have a negative charge flowing from terminal 1 into terminal 2. This is why our value is negative. So that is the actual technical explanation of what's going on. We have to look at voltage drop, rise, and the charge flow. So after we plug PC into a calculator, we are going to get 210 as our answer. Next, we have PD, or power D, and we're going to look at this. We have a 1.2 times 20. So these are both positive. We're just going to look at our current. D is over here. We know that our current normally goes into our positive and out of our negative. So this is what our voltage goes into the positive and out through the negative. So this is what our voltage is going to look like. And we know that our current is going this way. Since they're going in opposite directions, our D is going to be negative. So we'll put a negative sign out here to indicate delivery. And then we can put our 1.2 times 20 inside of here. Plugging this into a calculator, we are going to get negative 24. Next, back up here, we have E, and E is located right here. We have both positive values, so we're just going to look at our circuit. We know that our voltage goes in through the positive and out of the negative, so our voltage is going to look like this. Our current is going in the same direction, like this, so that means we're going to have a positive right here. I'm going to start writing it right here, that way we have more room. So our P of E is equal to a positive, and then 1.8 times 30. This is going to give us a 54 for P of E. Now we can start looking at P of F. For P of F, we have two negative values. We have a negative voltage and a negative current. Since our voltage drop is going from terminal 2 to terminal 1, it's going to go from negative into positive since we have a negative value. And then since our current is a negative charge flow from terminal 1 to terminal 2, that means that our current is going to be going this way, or the part that matters is going to be going this way. So that means for F, we are going to have a negative value since our voltage and our current are going in opposite directions. So we're going to have a negative right here, and then in parentheses our 1.8 times 40. Next we have G, and G we have again two negative values. So we are going to have to go from negative to positive. This is how the voltage drop works. If we have a negative value, instead of going from terminal 1 to 2, we go from terminal 2 to 1. And then we have our current, which is normally, it's going this way, but the part that matters is actually going down. We're reversing it. So our current is going to be going in this direction. We know that they're going in the same exact direction, so our P of G is going to be equal to a positive, and then in parentheses we have our values, and that leaves us with a 108 right here. And next we have a P of H, and we have a positive voltage and a negative current. Looking at H, we know that since we have a positive voltage, we are going in through the positive side and out of our negative side. We have our current, which is a negative 20. That means we are going to flip basically the direction, the part that we're looking at, to go this way. We can see that they're going in opposite directions, so we're going to have a negative out here, and then our values inside, which is 3.2 and 20. Plugging this into a calculator, we are going to get 64 as our answer. We can't forget the negative, so we have to make sure we have to add that out front as well. I also forgot the negative in my P of F right here. I put it right here, but I totally forgot it there. So we have to make sure that we have that out here as well. Same thing with P of A. I have my negative out here, but totally forgot it right here. So I'm gonna just add this in here like this. So we have a negative. This should be a negative, which is good. Positive, negative, positive, negative, positive, negative. And then we will see what the last one is. We have PJ lastly. We have a negative voltage and a positive current. When we look at J, since we have a negative voltage, that means we're going in through the negative side. And we have a positive current, so we're just going to look at the current that we're given. We can see that they're going in the same exact direction, so this is positive. That means our P of J is going to be a plus, and then we have our values in parentheses, which is 2.4 times 30. We can plug this into a calculator where we have 72. And then to check if our circuit diagram actually gave us the correct answer, we need to add all of these together. If we do not get 0, that means we got something wrong. Because again, remember, when we have a valid circuit or valid table, we need to have the power that's being delivered equal to the power that's being absorbed. So if we have a little circuit here, the power being delivered must equal the power that's being absorbed. So this is delivered, this is absorbed, and they must be equal. So they must both, when we add them together, be 0. Putting all these into a calculator, we got that all of this equals 0. So this is the work and answer for this problem.